stick with you. For me, it's always been the replicator. That magical device from Star Trek and other shows, right? The one that can
Yo,
just conjure up, I don't know, a gourmet meal, a fresh cup of tea, Earl Grey, hot, or even a spare starship part, basically, from thin air. It's the ultimate poof, there it is machine, and honestly, who wouldn't want one? But here's the burning question, the one that always pops into my head. Could it, actually be real? So today, we're diving deep into your sources on replicator technology, constraints on energy to matter conversion. Our mission to peel back the layers of sci-fi fantasy, basically, and explore what physics truly says about turning pure energy into matter. We'll look at the theory, the immense practical challenges, and where the real-world future of creation might actually lie. It's going to be a fascinating journey, I think. Some pretty mind-bending science ahead.
it absolutely is. Yeah, the allure of just
Ace.
effortlessly creating anything. It's incredibly captivating. And the idea itself, it touches upon one of physics' most profound principles. But what's truly fascinating, and maybe a bit daunting, is that while the concept is rooted in that fundamental principle,
Yeah.
the scientific constraints are equally profound. So yeah, we're in for a rigorous, but I agree, genuinely awe-inspiring look at the universe's rulebook.
Okay, and to really get our heads around this, we have to go straight to the big one, right? Einstein's NCMC theory. It's not just a formula you see on t-shirts. It's a really profound statement about the universe. It essentially tells us that mass and energy aren't separate things, but two different forms of the same fundamental stuff. You can actually think of mass as highly concentrated or congealed energy. Is that fair?
That's a great way to put it.
Hmm.
Congealed energy, yeah, precisely. And the key player in that equation, the part that really dictates the practical reality for any kind of replicator, is the SIA. That's the speed of light squared. What's critical here isn't just the number itself, but its immense magnitude. It's huge. It means that even a tiny, tiny amount of mass, like a single gram, holds an extraordinary amount of energy. So if you flip that around to create even a tiny speck of matter, you need an almost unimaginable concentration of energy.
Wait, okay, so when we talk about unimaginable, what kind of energy are we actually talking about? To make, say, just 1 gram of matter, that's barely a paperclip.
Yeah, it's staggering. For just one single gram of matter, you need 9.0010 joules of energy. To put that into perspective,
Yep.
that's roughly equivalent to the energy released by the atomic bomb dropped on Nagasaki. It's actually about twice the energy of the Hiroshima bomb. Or, if you want a more maybe civilian comparison, it's what a massive 1 gigawatt nuclear power plant would produce if it ran flat out continuously for nearly 3 years.
3 years for 1 gram, wow.
All for 1 gram. So the core insight here, the really key takeaway, is that the challenge isn't just generating that total amount of energy, though that's hard enough. It's about energy density. Matter is an incredibly compact form of energy, meaning any creation process would need to concentrate those vast amounts of energy into an infinitesimally small volume, almost a microscopic point, just to kickstart the creation of particles. This isn't just a challenge of building bigger power plants, it's a monumental problem of microscopic energy localization. That distinction is absolutely critical when we think about building a replicator.
That's a powerful point, and it makes sense given that staggering energy cost. I wonder if people often try to find simpler ways around it, to imagine matter creation. I've seen some ideas mentioned, maybe in less rigorous sources, about channeling electricity into some kind of diffuser or a nanoscale energy filter. The idea seems to be it follows some complex path, loses conductance, and then somehow stabilizes into matter. It sounds, well, deceptively plausible on the surface, doesn't it?
It does, yeah. It sounds sort of intuitive if you don't dig too deep.
Yeah.
But when you apply the fundamental laws of physics, this idea, unfortunately, well, doesn't really hold up. The nature of electrical energy in a circuit is completely different from the incredibly concentrated high-energy quantities you need to create actual particles. Think about it. Electrical energy in your wall socket, it's essentially the collective movement of relatively low-energy electrons. A single electron in your household wiring, for example, carries an energy of only a few electron volts, EV. Very small.
Okay, a few EV, and how much do we need?
Right now, here's the crucial mismatch. To create even the lightest stable particle we know, an electron, you first need to create its antimatter twin, a positron, at the same time. You always get pairs. This process, it's called pair production, and it requires a minimum energy of 1.022 million electron volts, 1.022 MeV. So that electron shuffling along in a wire, it has an energy roughly a million times too low to even begin this process. Not even
A
close.
million times.
Okay. And the terminology itself, like diffuser or loss of conductance, it's actually misleading here. What does loss of conductance mean? It means increased resistance. And what happens when electricity flows through a resistor?
It gets hot.
Exactly.
Hmm.
It dissipates energy as heat. And heat is the ultimate form of disorganized energy, spread out randomly among countless atoms. An infinitely complex path, as sometimes described, would simply be a very, very efficient resistor. It would maximize the conversion of organized electrical energy into disorganized heat, the exact opposite of the extreme concentration and organization required for matter creation. So you're essentially trying to use a system designed to spread energy out to achieve a goal that demands extreme energy concentration. Just doesn't work.
Got it. So it's like fundamentally misunderstanding the physics involved. The electrical diffuser is a category error trying to solve a quantum physics problem with classical electricity concepts. Okay, so that path is a dead end. But here's where it gets really interesting. Even though that idea doesn't work, we can actually make matter from energy in the real world. It just looks absolutely nothing like a sci-fi replicator. How do we actually do it?
You're absolutely right. The conversion of energy into matter isn't sci-fi. It's a well-established phenomenon. We see it in labs, we see it in nature. It's been observed and verified in high-energy physics for decades. The primary mechanism is called pair production, like we just touched on. Imagine a really high-energy photon, like a gamma ray pure energy, right? When this photon interacts with a very strong electromagnetic field, typically one found near a heavy atomic nucleus, it literally vanishes. Poof. Its energy is then converted into a particle-antiparticle pair, most commonly an electron and its antiparticle, a positron.
So the photon disappears and matter appears?
Basically, yes. But this isn't some kind of free-form creation. It comes with very strict rules. First, that photon must have energy equal to or greater than the combined rest mass energy of the two particles it creates. For an electron-positron pair, that minimum is 1.022 MeV, as we said. And second, crucially, it must happen near a massive object, like that atomic nucleus. Why?
To conserve momentum.
Exactly. The nucleus absorbs some recoil. A lone photon can't just split into matter in empty space. The math doesn't work out for conserving both energy and momentum. And if you look at the energies involved for heavier particles, say creating a proton and an antiproton, you need over 1.8 billion electron volts. That's over 1,800 times more energy than for the electron-positron pair.
Okay, so it's real, but it's a very specific, very high energy event,
Yeah.
not just flipping a switch. And we've even learned to sort of force this to happen ourselves, right? Though on a much, much more violent scale.
That's right. Our most powerful tools for doing this deliberately are particle accelerators, like the Large Hadron Collider, the LHC at CERN. Instead of starting with photons, these machines take existing particles, often protons, and accelerate them to incredible speeds, near the speed of light. This gives them immense kinetic energy. Then they smash these particles into each other, head on. These collisions create what you could call microscopic fireballs, where that enormous kinetic energy gets converted into showers of new particles, often exotic ones we don't see every day, and their corresponding antiparticles. This is how we've discovered things like the Higgs boson. That required collision energies up in the trillions of electron volts, 13.6 TeV, I believe. We've even experimentally confirmed processes where two high-energy photons collide directly to create matter, the Breit-Wheeler process. But again, you need photons in the MeV range, gamma rays, essentially.
And I read somewhere that even the empty vacuum isn't truly empty either, not in extreme conditions anyway.
That's a fascinating insight from quantum field theory, yeah. The vacuum isn't truly empty. It's this sort of dynamic sea of virtual particle-antiparticle pairs, constantly flickering in and out of existence. It's weird. And under extreme conditions, like right near the edge of a black hole that's related to Hawking radiation or extraordinarily strong electric fields, which is called the Schwinger effect, this vacuum energy can actually be converted into real particles. But, and this is the really consistent thread through all of this, all these known mechanisms, pair production, high-energy collisions, weird vacuum effects, they are fundamentally violent, probabilistic, and chaotic. They produce a spray, a jumble of particles and antiparticles, not a precisely ordered, stable structure like a cup or a tool. This chaotic character is completely, well, antithetical to the controlled, deterministic process implied by the term replicator.
Okay, this is building quite a case against the replicator. We've established the energy cost is astronomical, just fundamentally huge. And the actual ways we know energy turns into matter are violent, messy, and produce pairs of particles and antiparticles. But let's just imagine for a second. Let's say we waved a magic wand, solved the energy issue somehow, and we're churning out particles. What happens then? You can't just get a neatly formed steak or a new phone from a chaotic spray of subatomic particles, can you? This brings us to, it sounds like, even more fundamental hurdles that seem to make the sci-fi replicator truly impossible.
You hit on a really crucial point there.
Yes.
Even if the energy problem were completely waved away, the creation of a complex, stable object made of ordinary matter from energy faces this cascade of further obstacles. Obstacles rooted in the most fundamental laws of physics. The challenge extends far, far beyond simply converting energy into mass. It's not just step one.
Okay, like what? What's the next wall we hit?
Well, the first big one is what we could call the conservation law gauntlet.
Hmm.
Particle interactions, every single one, are governed by incredibly strict accounting rules, laws that cannot be broken. For example, electric charge must always be conserved. Total charge before has to equal total charge after. Since pure energy, like a photon, is electrically neutral, charge zero, any particles created from it must also have a net charge of zero when you add them up. This is why pair production always creates a particle and its oppositely charged antiparticle, like a negative electron and a positive positron, net charge zero.
Right, okay, charge neutrality. Makes sense.
But it gets even deeper and more problematic for replicators. There are also conservation laws for things called baryon number and lepton number. Baryons are particles like protons and neutrons, the stuff that makes up the nuclei of atoms. They have a baryon number of +1. Leptons include electrons. They have a lepton number of +1. Pure energy has 0 baryon number and 0 lepton number. So just like with charge, these numbers must also be conserved in any reaction. This means you fundamentally cannot create a proton, baryon number +1, from pure energy, baryon number 0, without also creating an antiproton, baryon number 1, to balance the books. Same goes for electrons, lepton number +1, and positrons, lepton number 1. So think about it. A replicator designed to produce an object made of ordinary atoms which are built from protons, neutrons, electrons is therefore fundamentally forbidden by these conservation laws from creating net baryonic or leptonic matter. It has to create the antimatter counterparts too.
Whoa, okay, hold on. This leads directly to a truly terrifying practical consequence, doesn't it? The matter-antimatter asymmetry problem, as the sources call it. So any replicator, by the laws of physics, must produce equal amounts of matter and antimatter.
Absolutely. That's the inescapable conclusion from the conservation laws. Any process starting from pure energy that creates matter must create an equal amount of antimatter. So let's revisit your 1-gram paperclip, or maybe something tastier like a 1-kilogram replicated steak.
Replicate.
By necessity, the replicator would also simultaneously produce 1 kilogram of anti-steak, made of antiprotons, antineutrons, and positrons. And what happens when matter and antimatter meet?
Boom. Annihilation.
Total annihilation. They instantly convert all of their combined mass back into a devastating burst of high-energy gamma radiation. Pure EMCSD. Your replicator wouldn't just be a convenience, it would effectively be an extraordinarily hazardous device, simultaneously creating your desired product and a perfectly matched quantity of what amounts to high explosive. The technological challenge of safely containing, manipulating, and then disposing of macroscopic quantities of antimatter. I mean, we can barely handle minuscule amounts in labs today. It's currently completely insurmountable.
That's sobering.
It is. And this challenge, this required symmetry, actually reflects one of the deepest unsolved mysteries in cosmology. Why is our universe made almost entirely of matter? According to the standard model and these conservation laws, the Big Bang should have produced equal amounts of matter and antimatter. They should have then mostly annihilated each other, leaving behind a universe filled mainly with radiation and very little matter. The fact that we exist, that planets and stars made of matter exist, implied some subtle unknown physics process in the very early universe must have violated these conservation laws slightly, creating a tiny excess of matter over antimatter, maybe one extra matter particle for every billion pairs. For a replicator to work as imagined in sci-fi creating only matter, it would somehow need to harness and control this universe-forming physics, this baryon number violating process. That's far beyond anything we can currently even theorize concretely, let alone engineer.
That is truly a mind-bending problem. Okay, so physics forbids net matter creation. Got it. Huge roadblock. But let's keep pushing the hypothetical. Beyond just the physical creation, there's another hurdle mentioned in the sources, one that seems to challenge the very act of copying or replicating itself. That's the quantum information challenge.
Yes. This takes us into the weirdness of quantum mechanics. This is where the no-cloning theorem comes into play. It's a fundamental principle, mathematically proven within quantum mechanics, stating that it is absolutely impossible to create an identical, independent copy of an arbitrary, unknown quantum state. Now, what does that mean for replication? To truly replicate a physical object like that steak again, you'd need to perfectly scan and copy the complete quantum state of every single particle it's made of.
That includes its exact position, its momentum, its spin orientation, its energy level, and crucially, its entanglement, its quantum connection with every other particle in the state. The no-cloning theorem says, nope, can't do that if you don't already know the state perfectly. You can't just scan an unknown quantum system and make a perfect clone.
So you can't just scan my favorite mug and print out an identical one.
Not if by identical you mean identical down to the quantum level. The theorem fundamentally forbids that kind of quantum Xeroxing. This forces us to completely redefine what a replicator could even be, scientifically speaking. It couldn't be a copier or duplicator in the way we normally think of copying. Instead, it would have to be more like a fabricator, essentially, an incredibly advanced atomic-scale 3D printer. Such a device wouldn't scan an existing object. It would need a complete pre-existing blueprint, a dataset describing the object down to the quantum state of every single particle. Then it would construct a brand new object that matches that blueprint from raw materials, or maybe from that matter-antimatter spray if we ignore the other problems. This distinction isn't just semantics, It touches upon really deep and still debated questions about the fundamental nature of information in physics and what it means to know or specify a state.
Okay, so it's not a copier, it's a super precise builder working from an unimaginably detailed blueprint. But even if we cracked all these staggering issues, we have the energy, we somehow manage the antimatter, we have the perfect quantum blueprint, there's still the monumental assembly challenge, isn't there? How do you actually go from that blueprint and a cloud of fundamental particles or even precisely created individual atoms to, say, a hot cup of coffee or a complex piece of technology or, heaven forbid, a living organism?
This is where the computational and engineering impossibilities really just pile up astronomically. First, think about the sheer computational complexity. Accurately simulating the quantum mechanical behavior of even a relatively simple molecule requires vast supercomputing resources today. Now imagine a macroscopic object, like that cup of coffee. It contains something on the order of Avogadro's number of particles. That's 6 followed by 23 zeros. 600,000 billion particles. Calculating the complete quantum blueprint for such a system, tracking the interactions, and managing the assembly process in real time, it would require a computational device of literally unimaginable power and stability, something far, far beyond anything currently conceived. Even theoretical quantum computers might not be up to the task for complex objects.
Just the data storage alone.
Exactly. And then there's the actual physical assembly itself, sometimes called mechanosynthesis or positional control. You'd need to precisely bind quarks together into protons and neutrons with quantometer precision. That's 10 in your meters, the size of a proton itself. Then assemble these into specific atomic nuclei, add the right electrons and the right orbitals to form specific atoms, then carefully bond these atoms into complex molecules, and finally arrange trillions upon trillions of these molecules into the specific, complex macroscopic structure of the coffee cup and all. This implies a technology akin to the futuristic concept of a molecular assembler or nanofactory, but one operating at the subatomic level with maybe picosecond, trillionths of a second, timing accuracy and femtometer precision. Our current technologies for manipulating individual atoms, like scanning, tunneling microscopes, are amazing tools, but they operate on much, much slower timescales and can only handle very simple structures compared to this.
So it's just layer upon layer of impossibility.
It really seems that way based on current physics. To summarize the journey from raw energy to a finished, complex object, it's not a single step. It's more like a hierarchical series of near-insurmountable obstacles. You have a fundamental physical impossibility regarding net matter creation due to conservation laws. You have an information-theoretic impossibility regarding cloning quantum states. And you have an utterly staggering computational and engineering impossibility regarding the actual assembly process.
Wow. Okay. This deep dive really paints a stark picture. It shows us pretty clearly that the classic sci-fi dream of converting raw energy directly into a complex, stable object well, it isn't compatible with our current, very well-tested understanding of physics. The replicator, as depicted in fiction, truly seems impossible under the known laws of the universe. So what does this all mean for the future of making things, for advanced manufacturing? If we can't literally create matter from the void, what's the next best thing? Where do we go from here?
You've captured it perfectly. This analysis, while maybe bursting the sci-fi bubble a bit, actually points us toward a more scientifically plausible, though still incredibly ambitious, paradigm for advanced manufacturing. It's not about creating matter from nothing, from the void. It's about achieving incredibly precise, programmable control over the matter that already exists all around us.
This fundamentally reframes the problem. It shifts it away from the domain of high-energy particle physics and firmly into the realms of chemistry, material science, nanotechnology, and robotics, all operating at the atomic and molecular scale.
I see. So instead of snapping our fingers and making a sandwich appear from energy, we're talking about building it, maybe molecule by molecule, from existing ingredients, atoms, essentially. That still sounds incredibly futuristic, maybe like nanobots building things, but it's a different kind of futuristic. It feels more grounded.
It is, exactly. It's a future that, while challenging, seems firmly grounded in potentially achievable science and engineering, even if it's decades or centuries away for complex things. This vision includes concepts like molecular assemblers. These hypothetical nanoscale devices that could build products molecule by molecule or atom by atom from a feedstock of existing raw materials following a programmed design. And we have natural examples. Our own biological ribosomes inside our cells are essentially natural molecular assemblers. They constantly assemble incredibly complex protein molecules from simple amino acid building blocks following instructions from our DNA. Nature proves the principle works. Now, creating synthetic, general-purpose assemblers that can build arbitrary structures, that faces enormous technical challenges, control, error correction, energy supply, but it's a coherent and physically grounded research direction.
Okay, so assemblers are the long-term dream. Is there anything closer, anything happening now that points in this direction?
Yes, definitely. We even have real-world technology moving steadily in this direction today, albeit on a much simpler scale for now. It's a technique called atomic layer deposition, or ALD. This is a manufacturing process used quite widely in things like microelectronics. It builds up thin films of material by depositing literally one atomic layer at a time in a very precise, self-limiting chemical cycle. You get incredible control over thickness and composition. And while ALD was traditionally used for creating uniform, flat coatings, recent advances, particularly in what's called area selective deposition, or ASD, are essentially turning ALD into a true nanometric 3D printing technique. It allows researchers to print different materials with atomic precision in the vertical dimension and with increasingly fine resolution horizontally, building up complex nanoscale structures layer by layer. This technology, ALD and especially ASD, really represents the current state-of-the-art in practical atomic scale fabrication. It provides, I think, the most realistic pathway, the clearest trajectory, toward a future of truly atomically precise manufacturing.
That's truly fascinating. So it sounds like the real replicator, the ultimate device for making things on demand, won't be some mystical device based on EMCR and particle physics that makes things from raw energy. Instead, it'll likely be the culmination of nanotechnology and material science, a highly advanced nanofactory, maybe using techniques evolved from ALD or molecular assemblers, building incredibly complex things with atomic precision, but using existing atomic and molecular building blocks. It's still almost like magic from our perspective today, but maybe a magic we might actually achieve someday.
Exactly. That seems to be the scientifically plausible route. It shifts the dream from violating fundamental laws to mastering the assembly of matter that already exists. And, if we connect all this back to the bigger picture, this profound understanding of how constrained matter creation from energy really is, it raises an important question for us all to think about, maybe. If the fundamental act of creation from raw energy is so incredibly difficult, so hedged about by the strict laws of the universe, how does that change our perspective on the very nature of creation itself? Whether we're talking about the universe's origins or biological life, or even our own human acts of making and building, it's a thought that truly gives you pause, doesn't it? Makes you appreciate the matter we already have.